you for the introduction. And good afternoon, everyone. My name is Lara, and I'm from the University of Padova. And this is a research that we have done in collaboration with the University of Bolzano about the multiphysics simulation of cyclic voltammetry response in flexible devices. So first, a quick outline of the presentation. First, I'll give you some context about this research, and then I'll show you our proposed devices and layouts. And then I'll briefly give you some explanation about our developed multiphysics model, and I'll give you some results that we have created from the simulation, and then I'll move with some final remarks on perspective. Is it working? Yeah?
Yes.
Okay, perfect. So at first we wanted to design this flexible screen printed technology for, in particular, detecting biomarkers in sweat. But then we asked ourselves, how does the electrode design influence the sensor performance? And to answer that, we used multiphysics modeling, which is a very powerful tool since we can design the layout even before the fabrication, and also optimize the sensor for a final application. In this case, we have optimized the surface coverage through functionalization study. And also through modeling, we can also study the electrochemical phenomena in depth, also modeling what's happening even at microscopical level. So, multiphysics modeling is also quite challenging because you need to consider a lot of very different but interdependent phenomena that are happening. In fact, you need to take into account the electrochemical metal-solution interface and what's happening around them, and also the redox reaction, the terminal currents and the potential in both solid and fluid state, and also how the measurement is performed. In fact, you need to take into account how the signal is generated and the readout signal, so through the potentiostat. We are indeed in need of a synergetic multiphysics modeling, which needs a proper calibration of the parameters with the materials and the experimental setup that we are including. And also we need specific equivalent circuit to model the potentiostat that is running the measurement. So first, we fabricated the devices, which are screen printed on flexible PET substrate, and the devices have a conventional 3-electrode structure with a carbon counter electrode, a carbon working electrode, and a silver chloride reference electrode. The metal tracks were made in silver, and finally, on top of the structure, we put the electrode insulator to delimit the electroactive area. We also characterized the surface through SEM imaging. In fact, here we can see a picture of the ink that we used. In this case, is the working electrode. The small flakes are the carbon black, which is one of the components of the ink, and the bigger flakes is the graphite, the other component of the ink that we used. We also studied the thickness of the device, which is around 5.7 micrometers, with a roughness of around 60%. So, to redesign from this configuration different layouts by changing the distance between the counter and working electrode and the area of the working electrode and the counter electrode. So these are the 4 proposed layouts that we test. The design A as the bigger working area and counter area. Meanwhile, the design B, C, and D have the same working and counter area, but are decreasing distances between the electrodes. So the multiphysics modeling is developed in Compton Multiphysics and is a 3D finite element model where each layout is imported as a geometry in the model, and it's characterized by specific material properties. It also finally meshed, since we need fine meshing with a good refinement to solve the system of equation with a finite element method. So the model includes different physics, which are interdependent to each other, The first one models the interface current through the Bajramshahe equation. Then we model the redox reaction at the interface through the Nernst equation, and the diffusive transport through the fixed laws, of course. And then the electrical currents models the currents and the potential in the metal contacts and the tracks. And finally, we have designed equivalent circuit of an ideal potentiostat to model how the input signal and the readout are made. And if you want more detail on about this model, you can check this our final paper about it here. So the model actually needs to be calibrated with experimental measurements, which and then we have to retrieve the model parameters, which are dependent from the lecture's materials and experimental condition. In fact, we have identified these 5 parameters that are the main one of the model. The redox equilibrium potential, which is retrieved by Cyclic Voltammetry curves, and it is dependent on redox solution and, of course, the reference electrode that we use. The double layer capacitance in this case is extrapolated by fitting CPE modified Randall's circuit on the impedance spectroscopy measurements, and it is estimated from the constant space element, of course. The double layer capacitance is dependent on the electrolyte and the area, and to avoid this dependency, we actually normalize the value. Then the diffusivity coefficients are dependent on the redox species of the electrolyte solution, of course, and they are retrieved from literature. And then the apparent transfer coefficient is an indicator of how much reversible is the redox reaction. Meanwhile, the last one is the exchange current density, which is calculated from the charge transfer resistance, and it's dependent on the redox solution and the material that we used on the electrode. So, as we just saw, the model parameters are not dependent on the geometry. So we can keep the parameters fixed and just play with the layout. And so we calibrated the model using just layout C. So what can we know through simulation? About the different areas, if we take a look to layout B, C, and D, they have indeed similar current peaks, which is actually fine because they have the same working area. But while we take a look at layout A, we can see that the experimental current peaks are much lower than the simulated one. And why so? Because we are, of course, expecting at least a 4-fold higher current peak for the layout A. Since if we take a look to the random substitute equation, the current peaks should be proportional to the area of the electrode, which is 4 times higher than the other layouts. So why there is this difference between the experimental measurement and the expected one, the simulated one? To understand that, we normalized the current, and we saw that with a large working area, the current density was indeed lower than the smaller one for the experimental values. And we thought that this was due to the fabrication process. So a large working area may be more affected by impurities, more roughness, and defects, and porosity on the electrode. Meanwhile, by taking a look to the simulated currents, we can see that the values are almost comparable for all the layouts, which means that even in theory, a large working electrode may not actually contribute to enhance the device performance, but and this further confirms the fact that the signal is heavily dependent on the material properties. And about the different distances, we can see that while decreasing the distance between the working and counter electrode, we can see a higher peak. And this is even more visible by looking at the current density at the working electrode. In fact, for the closest configuration, it's higher than the other ones. And why this difference? Well, lower working and counter distance may actually enhance the presence and availability of redox species at the interface, so around the working electrode, and so we have a shorter distance for the exchange of charges. between these two electrodes, which increases the current density. So just some take-home messages. The proposed model is used to predict and evaluate the cyclic voltammetry signal of different flexible devices. What we saw was that the surface impurities and roughness and porosity may actually affect the electrochemical signal, while a larger working area do not show a higher current density overall as in the electrode. And so this further confirms that the electrical signal is dependent on the material properties. And then we have this final very interesting point where we saw that a closer distance between the working and counter electrode may actually influence the electrochemical signal. So how can we choose which is the best or most suitable design for our application? Well, simulation can give us an idea on how to choose. In fact, in future, we are planning to include also impedance spectroscopy simulation to better understand what's happening at the level of charge transfer and at microscopic level. And also we are including the roughness and the porosity in the simulation to understand the influence on the signal. With this, I conclude, and if you have any questions, thank you for your attention.